Have you ever noticed how some words look the same forwards and backwards? Take the word level for example. If you read it from left to right, it says level. But if you start from the right and read it backwards, it still says level. This special kind of word is called a palindrome. It's like having a secret mirror right in the middle. Words like kayak, madam, and race car all share this neat trick. They are perfectly symmetrical, creating a sense of balance and order that our brains find quite pleasing. It's a simple idea, but it pops up in the most unexpected places, showing us that patterns can be fun and surprising. This idea of a palindrome isn't just limited to simple words. You can find it in whole sentences, too. A famous example is a man, a plan, a canal, Panama. If you ignore the punctuation and spaces and read it backwards, it says the exact same thing. It's a much longer and more complex example, but the basic rule is still there. There is a central point, a pivot, around which everything else is reflected perfectly. This concept of reading something the same way in both directions is the core of what makes a palindrome so fascinating and unique in the world of language. Numbers can be palindromes too, and this is where things get really interesting for a mathematician. Think about the number 121. Read it from left to right, and you get 121. Now, read it from right to left, and you still have 121. It works just like the word level. Other examples include 353, 4,884, or even a very long number like 9,102,019. These are called palindromic numbers. They have a beautiful built-in symmetry. It's as if the numbers are looking at their own reflection in a mirror, and we get to admire the perfect match from the outside. The beauty of these palindromic numbers lies in their predictability and structure. In a world that can often feel chaotic and random, a palindrome offers a small moment of perfect order. It follows a simple, elegant rule that is easy to understand, yet it can create numbers of incredible length and complexity. Whether it's a short three-digit number like 101, or a massive number with dozens of digits, the principle remains the same. This satisfying symmetry is not just a curious trick, it's a fundamental pattern that we will see echoed in many other parts of our universe, from the smallest particles to the largest galaxies. This idea of symmetry, the very thing that makes a palindrome special, is not just a human invention. Nature is absolutely filled with it. Just look at a snowflake. Each one is a unique and intricate crystal of ice, but they all share a common feature: six-fold symmetry. If you were to rotate a snowflake by a sixth of a full turn, it would look exactly the same as it did before. It's as if nature used a mirror to create each of its 6 arms, reflecting the pattern perfectly around a central point. This is nature's version of a palindrome, written not in letters or numbers, but in frozen water. You can see this principle of symmetry in living things too. Think about a butterfly. The patterns on its left wing are a near-perfect mirror image of the patterns on its right wing. This is called bilateral symmetry, and it's incredibly common in the animal kingdom. Humans, dogs, fish, and insects all have this left-right symmetry. It helps animals move in a balanced and coordinated way, whether they are flying, swimming, or walking. This natural balance is a form of physical palindrome, where one half of a body reflects the other half across a central line, just like the two halves of the number 88. Even on a much smaller scale, deep inside our own bodies, we find this same commitment to symmetry. The famous DNA molecule, the blueprint for all life, has a palindromic structure. It's a double helix, like a twisted ladder. The sequence of chemicals, or bases, on one strand corresponds to the sequence on the other strand in a specific reflective way. This structural symmetry is crucial for how DNA copies itself, allowing life to replicate and continue. It's another example of how a simple, elegant pattern, like a palindrome, can be the foundation for something incredibly complex and vital. Beyond our planet, the universe itself seems to love symmetry. The orbits of planets around a star often form stable, predictable ellipses. Many galaxies, including our own Milky Way, have beautiful spiral arms that curve out from a central point in a symmetrical fashion. These large-scale patterns suggest that the fundamental laws of physics that govern the cosmos have an inherent sense of balance and order. From the tiny snowflake to the vast spiral galaxy, nature seems to be whispering the same secret. Symmetry is a fundamental building block of the universe, a cosmic palindrome written in stars and stone. Now, let's shift our attention from the world of reflections to a different kind of number, one that is defined by its loneliness. These are the prime numbers. A prime number is a whole number greater than one that cannot be formed by multiplying two smaller whole numbers. In other words, its only divisors are 1 and itself. The number 7 is a great example. You can only get to 7 by multiplying 1 by 7. You can't multiply any other whole numbers together to make it. This makes it a prime. The number 6, however, is not a prime, because you can get to it by multiplying 2 by 3. Prime numbers are the atoms of the number world. They are the fundamental building blocks from which all other whole numbers are made. Any number that is not a prime, like 12, can be broken down into a unique product of prime numbers. For 12, that would be 2 times 2 times 3. This is called its prime factorization, and it's unique for every number. No matter how you try to break down 12, you will always end up with those same prime building blocks. This makes primes incredibly important in mathematics. They hold the secret code to all other numbers. As you look at larger and larger numbers, primes become much rarer. In the first 10 numbers, we have 4 primes, 2, 3, 5, and 7. That's 40%. In the first 100 numbers, there are 25 primes, which is 25%. By the time you get to the first 1,000 numbers, the percentage drops even further. They seem to spread out, becoming more elusive and harder to find. Mathematicians have been searching for a pattern to predict where the next prime number will appear for centuries, but no simple formula has ever been found. Their distribution seems almost random, which makes them both frustrating and fascinating. This combination of being fundamental yet mysterious is what makes prime numbers so special. They are the essential ingredients for all of mathematics, yet they follow no obvious rules. They are simple to define but incredibly difficult to predict. This blend of order and chaos is not just a mathematical curiosity. As we will see, this very property of primes makes them incredibly useful, not just in theory, but in the real world. Their lonely, indivisible nature gives them a special kind of strength that both nature and humans have learned to rely on in surprising ways. It might seem strange to think that prime numbers could appear in the natural world, but they do. One of the most famous and baffling examples is the life cycle of the periodical cicada. These insects spend most of their lives underground, only to emerge all at once in massive swarms. What's truly remarkable is the timing of their emergence. Different broods of cicadas surface every 13 or 17 years. Both 13 and 17 are prime numbers. Scientists believe this prime-numbered cycle is an evolutionary survival strategy. It makes it very difficult for predators with shorter life cycles to sync up with them. Imagine a predator that has a life cycle of, say, 3 years. If the cicadas emerged every 12 years, the predator would be there to meet them every single time, since 12 is divisible by 3. But because the cicadas emerge every 13 years, the predator would only encounter them once every 39 years. 3 times 13. This prime number cycle helps the cicadas avoid being a predictable meal, giving them a much better chance of surviving and reproducing. It's a brilliant example of how a purely mathematical concept can provide a real-world evolutionary advantage. Nature, it seems, is a very clever mathematician. This idea of using primes to create hard-to-predict patterns is also the backbone of modern digital security. Every time you buy something online, send a secure email, or log into your bank account, you are using the power of prime numbers. The security systems that protect your information, known as cryptography, rely on a simple but powerful fact. It is easy to multiply two very large prime numbers together, but it is incredibly difficult to take that resulting large number and figure out which two primes were used to create it. This is the mathematical lock that keeps our digital lives safe. Your computer can take two prime numbers, each hundreds of digits long, and multiply them in a fraction of a second. The result is a massive new number that serves as a public key. But for another computer to work backwards from that massive number to find the original two primes, the private key, could take even the world's fastest supercomputers thousands of years. The difficulty of factoring large numbers into their prime components is the wall that protects your sensitive data. It's amazing to think that these lonely, indivisible numbers, once just a mathematical curiosity, are now the silent guardians of our global digital economy. We have explored the world of palindromes with their perfect reflective symmetry, and we have explored the world of prime numbers, the lonely and indivisible building blocks of mathematics. Now, what happens when these two fascinating worlds collide? What do you get when you find a number that is both a palindrome and a prime? You get something truly special and rare, a palindromic prime. These are the crown jewels of the number world, possessing both the beautiful symmetry of a palindrome and the fundamental integrity of a prime number. They are numbers that read the same forwards and backwards and can only be divided by one and themselves. Let's start with some simple examples. The number 11 is a palindrome and it's also a prime. So, 11 is our first two-digit palindromic prime. As we look at larger numbers, we can find more. The number 101 is a palindrome, and after checking, we find it's also a prime. You can't divide it by 2, 3, 5, or 7. So 101 is a three-digit palindromic prime. Others soon follow, like 131, 151, 181, and 191. Each of these numbers has that elegant, mirror-like quality, while also holding that stubborn, indivisible strength of a prime. Finding them is a two-step process. First, you identify a number that is a palindrome, like 353. This is the easy part, you just have to check if its digits are symmetrical. The second step is much harder. You have to test if that number is prime. For 353, you would need to try dividing it by all the prime numbers up to its square root, which is about 18. After checking 2, 3, 5, 7, 11, 13 and 17, you would find that none of them divided evenly. Therefore, 353 is not only a palindrome, but it is also a prime number, making it another member of this exclusive club. The existence of these numbers bridges two very different mathematical ideas. Palindromes are about structure, form, and visual pattern. They are defined by the arrangement of their digits. Primes, on the other hand, are about a deeper, more abstract property, their indivisibility. They are defined by what they are not. They are not the product of smaller numbers. A palindromic prime, therefore, is a number that satisfies both a rule of external form and a rule of internal substance. It's a number that is beautiful on the outside and fundamentally strong on the inside. While finding a few small palindromic primes like 11 and 101 might seem straightforward, the hunt quickly becomes incredibly difficult. As the number of digits increases, palindromic primes become astonishingly rare. Think about it this way. As numbers get bigger, the primes themselves already start to thin out. At the same time, palindromic numbers are also quite specific. You can't just have any combination of digits, they have to be symmetrical. The chances of a number happening to be both a palindrome and a prime at the same time becomes smaller and smaller the larger you go. There's a curious rule that makes the search even harder. With the exception of the number 11, there are no palindromic primes with an even number of digits. A mathematical proof shows that any palindrome with an even number of digits is always divisible by 11. For example, the palindrome 1221 can be divided by 11 to get 111. The palindrome 4884 can be divided by 11 to get 444. Since they are all divisible by 11, they cannot, by definition, be prime. This means we can completely ignore all palindromes with 4, 6, 8, 10, or any even number of digits in our search, saving us some time, but also making the club even more exclusive. So, our search for palindromic primes must focus only on those with an odd number of digits, 3, 5, 7, and so on. The largest one that was known for a long time was a number discovered in 1951, often called Belphegor's prime. It's a 31-digit number 1 followed by 13 zeros, then the number 666 followed by 13 more zeros, and then a final one. It's a perfect palindrome and it is also prime. Finding such a number required immense computational power, and it gives you a sense of the scale of the challenge. We are truly searching for needles in a cosmic haystack. Today, with the help of powerful computers, mathematicians have found much larger palindromic primes, some with tens of thousands of digits. But each new discovery is a major achievement that requires sifting through countless candidates. The journey to find these numbers is a testament to human curiosity. It shows our desire to find order and special patterns even in the most abstract realms. The rarity of palindromic primes doesn't make them less important, it makes them more precious. They are like rare gems, beautiful and unique, because they are so incredibly hard to find. The intersection of palindromes and primes is more than just a mathematical game. It's a beautiful metaphor for the hidden patterns that govern our universe. The symmetry of a palindrome reminds us of the physical symmetries we see all around us in nature, from the balanced wings of a butterfly to the symmetrical arrangement of petals on a flower. This is the visible structural order of the cosmos. It's the beauty we can see with our own eyes. These patterns provide stability and efficiency, whether it's for an animal's movement or a plant's growth. This is the palindrome part of the equation of existence. The indivisible nature of a prime number, on the other hand, represents the fundamental, unbreakable laws of science. Just as all numbers are built from primes, all matter is built from fundamental particles like quarks and electrons. These particles are the primes of our physical world, the indivisible building blocks that cannot be broken down further. The laws of physics that govern how these particles interact are constant and unchanging. This is the hidden, internal strength of the universe. This is the prime part of the equation, the underlying substance that gives structure its meaning and integrity. A palindromic prime, therefore, is like a perfect meeting of these two cosmic principles. It represents a moment where visible beauty and fundamental truth align perfectly. Think of the symmetrical orbitals of an atom, where electrons exist in beautifully shaped, balanced clouds of probability, all governed by the strict, unbreakable laws of quantum mechanics. The shape is the palindrome, the laws are the prime. Or consider the perfect symmetry of a crystal, whose beautiful external form is a direct result of the unchangeable chemical bonds holding its atoms together in a rigid, repeating lattice. In the end, the study of these strange and wonderful numbers encourages us to look for connections and patterns everywhere. It shows us that the rules that create a beautiful number are not so different from the rules that create a beautiful universe. The joy of finding a palindromic prime is the joy of seeing a hidden symmetry, of uncovering a deep and elegant truth. So the next time you see a symmetrical pattern in a leaf, or admire the stars in the night sky, remember the palindromic prime. It's a reminder that our universe is not just random and chaotic, it is a place of profound beauty, hidden order, and cosmic symmetry waiting to be discovered.